Great. I think we're live, right? So I'm gonna start. So hey everyone, I'm Wei Dai, and I'm going to be talking about interoperability of crypto compute environments. So just by looking at the title, you might be wondering, what are crypto compute environments? And we'll get into that. So let's take a brief look at the history for blockchains. So during the Bitcoin era, we mostly did large-scale permissionless distributed consensus, and which was not possible before via proof of work. And kind of in my categorization, we have the proto-Ethereum era, which moved us to general smart contracts for both doing consensus on data and also general compute. And there are other advances such as proof of stake, and also using zero knowledge for instance, private transfers. And there's the modern Ethereum era, which sees kind of more specialization of different components and the rise of zero knowledge compute. So examples for this are, for instance, special data availability services. So for instance, that the Ethereum L1 is going to be used for data availability, or there's also like data availability committees that some chains will build. And also, for instance, rollups, both optimistic and zero knowledge. And we're, of course, seeing more ZK applications. And in my talk, I'm going to argue that looking forward to the future, we'll see more specialized compute environments, and applications will can utilize more of these special computing environments to gain more scalability and privacy. So let's get a little bit more into details to see what I mean by compute environments. So let's look at the example of developing a typical application on Ethereum, right? So we have two components. One, it's based in EVM, and most people will program Solidity, and that's on-chain components. And we'll have usually a front end and wallet components that is usually coded in JavaScript or TypeScript, with some wallet client holding the secret key, for instance, MetaMask, right? And the two are glued together via usually RPC calls, and there are libraries that help facilitate these both read and write onto smart contracts. And and there's really trade-offs between putting computation on one versus the other, right? So if you put computation on chain, it is fault tolerant and highly available, but it's relatively expensive. And also the data on chains is completely public. Whereas you could also put computation off chain to front end, and in general this computation is not verifiable, so you don't do transactions in the front end, but you can do a lot of cheap cheap computation, and you can hold secret data. I think these trade-offs are clear to every blockchain developer, but it is what you have to do when you design a blockchain app: what to put on chain and what to put in your front end. And now, since this is an OpenZL conference, and I'm sure people know about zero knowledge circuits, and so when you add zero knowledge circuit to the mix, effectively you now have three different compute environments, right? Whereas previously for on-chain logic, everything's public and it's verifiable because it's the entire computational trace. You can recompute it if you grab the historical call data, and for front end it's private, but it's not verifiable, right? You can't trust the front ends to do a computation correctly. With ZK, you get both succinct verifiability and the ability to do that on private data, on data that you don't reveal on chain, right? And there's a number of frameworks. For instance, Circom, it's a popular one, and of course OpenZL, it's another new ecosystem. And so now if you kind of have ZK in the mix when you design an application, it's really three different places where you can place your computation or your application logic, right? On chain, in front ends, or inside a zero knowledge circuit. And so the question I want to ask in this talk is really, what's the best way to do this? And is this like how much friction it is to design an application with all these different components? So let's run through this with a concrete example via a simple voting app, right? So the setup is we're going to have a set of people, which we call the voters, and each person is going to have a weight assignment. So this might be everybody had the same vote weight, or it might be some token-based voting. It might be quadratic. We don't care. In here, we have a function that abstracts that away. And there's three different things that the application will need to take care of, right? So we need to have people being able to cast votes, and a user should not be able to cast votes of another user, so therefore it should require the secret key. And there must be some form of vote validation, right? So we want this to be people cannot forge their votes; they can only vote once, and that the vote weight is actually correct. And finally, there's going to be some type of votes counting, right? So at the end, we'll tally all the votes, and because we want to know what is the output that we'll go forward with, right? So let's see how a typical on-chain voting application will be done. With just smart contracts and front ends. And a typical division will be that the front end is only going to do vote casting, right? So the it could be some form of signature from, for instance, MetaMask, and everything else will be done on chain. So this is just one example. We could do off-chain vote aggregation, but imagine in this case we're doing this entirely on chain. So the on-chain contract will keep track of who can vote and their weights, and as well as do all the vote validation and counting. So what would this look like? Just to be concrete with our example, we'll write a smart contract with the following interfaces. You will keep a map weights of for each voter, and you will have two interfaces: a validated votes and a count vote, right? And the front end will simply have this cast votes. So the top code is in Solidity, and the bottom code is TypeScript. And this might look relatively simple, but actually when you go on to implement it, there's subtleties, because a vote struct is going to be different in these two languages, right? So in this case, the top one will be in Solidity, and the bottom one is in TypeScript, and they actually there's different types for these things. And if you use a library like Ethers, it kind of maps nicely between the two. But if you do this by hand, sometimes you have code that tries to define the same data structure, but will live at two different places that you need to modify independently. So it's not ideal, but I think people have learned to work with it. So that's kind of the first big one I will mention. And then now let's. So what have we done here? We have designed a simple voting application with on-chain components and the front-end components. And of course, this is not voting is typically done, but I mean, it's actually kind of similar to how voting is done today, right? Like, on for instance, Snapshot, you can see everyone else's vote. But let's actually make this more private using ZK, because we're at an OpenZL conference. So what are we going to put the $0 circuits? Well, we're going to put some of the vote validation and vote casting logic into the $0 circuit, right? So we're going to move that from the on-chain logic into the $0 circuit. And so exactly what privacy are we trying to guarantee? Here, let's just say that everybody have the same weights, or for every single possible vote weight, there's many different voters, and we want to hide actually who's behind a single vote when we submit this on chain. So the first thing that we'll do is we're going to change this vote struct to, instead of announcing who the voter is, we're going to actually have an anonymous identifier for each voter. And the way we'll do that is so this will be similar to what was called the nullifier or notifying scheme. We simply hash the secret key for the voter and the voter, like public voter identifier, and to derive this anonymous voter string, right? And so what the circuit would do is make sure that this is computed correctly, that there's the anonymous voter actually have a single actual voter behind, and that actual voter behind this anonymous voter has enough has the right weight, right? So here the code is in quotes, because this in circle will not work. You will have to kind of commit to this mapping between voters and weights, and using Merkle tree, for example, and actually open it up. So but the code will the logic will look roughly like this. And of course, there's different code that you would need to write to make sure all of these things work. For example, in the front end, you need to write, how to connect generation, of the witnesses for the circuit, and the improving the circuit, and then constructing the final vote struct. And on the contract side, you will have, again, validated votes. Now this validation will kind of also verify the circuit, and we'll have a way to aggregate these votes, right? So you can see that this, as we move logic around, so recall we wanted to move some of the logic from on-chain to inside the knowledge circuit so we can protect the identity of the voter. But during that process, there's a lot more kind of gluing that we'll have to do in such application. And in fact, if you were to do an app with these 3 different interfaces and in Circom, there's just a lot of gluing code that you have to do to get this to work well together. So that's that. And let's do something more with our example application. Let's try to so one problem with this is that on-chain vote aggregation is very expensive. So every single vote is still being submitted on-chain, and and that's expensive if you do this on Ethereum L1. So let's just make this more cheaper and more scalable. And we'll do so by also using ZK. So previously we did this thing, which I will call client-side ZK, which means that it's taking in secret keys that the user has, and it's being run client-side. And we could, in this example, add a server-side ZK that doesn't take any secret information from users, but simply aggregates computation and do them in a verifiable manner so that they can be verified on-chain. So in particular, we'll be putting vote aggregation to inside this server-side ZK circuit. And some people also call this ZkZk rollup, right? So you have 2 layers of zero-knowledge circuits. The first layer to offer privacy, and the second layer to offer scalability. So I'm just going to be showing the server-side ZK circuit here. So in this circuit, typically, what will take input array of anonymous votes, and the circuit simply validate each vote and add and aggregate the votes based on their options, right? And additionally, there's kind of validity checks on these votes to make sure that's not a single, no one double voted. And again, these are in quotes because it's actually not easy to do in Circom. And so, for instance, if you use RNCS, then uniqueness check is actually quite hard. It might be a quadratic blow up in the number of votes that you have to do in constraints. But if you use Plonk, there's simpler ways you can check uniqueness of a set of values. And similarly, we'll have to modify our on-chain logic to be able to verify aggregated results from the server-side ZK circuit. Okay, so what have we done in shots? So there's a client-side ZK circuit that offers privacy, and the server-side circuit that aggregates votes, so we can get scalability. And so what the problem with this is that the first problem is the aggregation server can now censor votes. So this is a problem for pretty much for all rollups that have centralized sequencers, right? The sequencer could censor transactions, and in our case, the server could censor votes. And the second problem is you can do so by knowing the information of the votes, right? So you can just refuse to aggregate votes that vote for a certain outcome. This is, of course, not an ideal scenario, and let's try to perhaps get around these problems. And so let's consider what we do with a computational compute module that is available in this ecosystem. So what I mean by this is, so suppose we have the following black box that helps you do the following. So first, you're going to want to compute on some input, but instead of giving the input directly to this compute module, you encrypt it under some public key that's controlled by a set of consensus nodes. And you also need to give this compute module some type of function here called compute, and you release the output of compute on the input on the actual underlying input, but not the encrypted one, right? So and moreover, the computational compute module is controlled by smart contract. So the smart contract can say, you give me encrypted input, I'm going to compute some function on the underlying message, and I will get the output, right? So the input could be votes, and the compute could be just aggregation, and the output will be vote counting, the content votes, right? And so this is actually a really, really powerful tool that can be built, for instance, using fully homomorphic encryption or multi-party computation or trusted execution environments. So for the purpose of this talk, I'm going to assume that such a black box exists, as an on-chain service, and let's use it for our voting example. So what this will look like is the following. So first of all, we actually have to ensure that our votes are encrypted correctly into this on-chain compute module. And then inside the compute module, we'll actually write the aggregation code that simply loops over all the votes and add their weights, right? And then again, we'll have some on-chain verification logic that actually invoke this continuous compute. So as you can see, so basically every single time we try to move a piece of the application logic to somewhere, there's a lot of changes required around all the other components to be able to interoperate with that. And as you see here, so the code for the compute is written in this imaginary language that is similar to Solidity and plus Circum. But such a tooling infrastructure that actually doesn't exist currently. Well, also the computes are generally I guess not a general component that's available in every blockchain ecosystem. But this talk is future looking, and let's think about what are the possible tools we could use. And out of all the components that we have discussed previously in the voting example, so this is roughly the picture. And actually, I'm going to divide this further, divide the front-end logic further to front-end logic that does not require a secret key, and wallet logic that actually requires secret key. And so the different components will roughly look like this. So on the bottom right, you have kind of everything that takes in user secrets. So secret keys or secret information, right? And the code is run entirely on user's device in a secure manner. And on the top left, you have kind of on-chain computes, things that's controlled by consensus. We have high availability and fault tolerance. And and then kind of in the middle there, we'll have kind of infrastructure around this that we don't need to place as much trust. And this, you can maybe call them the typical Web 2 components, right? So okay, so there's a lot of different components, and almost every components have different ways that you would program. And the key part is actually the connections between them. It's what generates most of the friction. Right, so for some of these connections, for instance, between front-end and on-chain, and for interacting with general circuits, both proving and verifying, there's frameworks that do so better than others. This is not because of the fundamental technical advantage, but more just that it's better tooling around the ecosystem. So for instance, Ethers or Circom StarkJS ecosystem has picked up a lot more usage just because they're easier to use. And so for something like connection between the client-side ZK and server-side ZK, there's less tooling. For instance, because it requires recursive proof aggregation, and there hasn't been. I guess maybe with the exception of Plonky 2, there hasn't been like a really easy to use framework to do that, to program both the client-side circuit and the server-side circuit. So since we're a bit short on time, I'll perhaps speed through this slide. So the gist is that there's different environments, and I want to ask the question of how much code can actually be shared between these environments. And on the high level is that the answer might be, there's fundamental incompatibility with these environments. So for example, for on-chain, you have different data types, right? Whereas, storage semantics. There's call data, there's memory, there's storage. And for general knowledge, there's fundamentally different ones, in particular, witness and public. But data layout can actually be potentially shared. So for instance, in the voting example, we could potentially have a common struct that kind of take the lowest common denominator between the possible data types. So for example, would be a field element, your proof system, right? And there could be a library that really just maps a common struct definition to all the different compute platforms like TypeScript and Solidity. And so here's kind of concluding remarks that I'll make. The picture, well, that I want to kind of help paint here is that there'll be more compute environments in ecosystem to come, especially around ZK and computational compute. And applications will be able to utilize the compute environments to build more special functionalities. And one main source of friction that I foresee is really the interoperability between these different compute environments. And eliminating this friction is going to be key to, I think, the success of the ecosystem, because it improves developer experience and user experience. And so, let's build tools that that help developers write applications this way. And that's the end of my talk. Thanks for your attention. Now I'll take questions.
Thank you very much, Wei. Yeah, we've got a little bit of time for some audience questions. So if anyone has any questions, feel free to ask in the comments section or the Q&A. All right, great. Yeah, if no questions, then we will move on to the final talk of session 2.